Welcome to our latest video, which has the title Revising AS Energetics. This video is suitable for both AS and A-level students. By the end of this video lesson, you should have an improved understanding of key energetics concepts covered at AS level, such as energy profile diagrams, enthalpy changes, and Hess's Law. And you should also be able to use and draw energy cycle diagrams applying Hess's Law to calculate enthalpy changes. So let's start this video by explaining what we mean by the term energetics. So energetics is the branch of chemistry that looks at the way energy is transferred during chemical reactions and is sometimes referred to as thermochemistry because in chemistry we're very interested in heat changes, and energetics is important because it helps chemists explain the stability of compounds and it helps them to predict the likely direction of chemical change. And with the help of energetics, chemists can predict whether chemical reactions are likely to occur or not. And in year 12, we looked at key energetic terms such as the standard enthalpy change of combustion and formation. And we also looked at Hess's Law and energy cycles and how we use these to determine enthalpy changes. Now, the aim of this video is to revise key concepts covered at AS level with regard to energetics. And we're doing this in preparation for year 13, where there are a number of topics related to energetics. So to revise these concepts, we're going to get you to attempt a few practice questions. So here are the first two practice questions. So read through the questions, pause the video, have a go at them, and then we'll go for the answers. So before we go through the answers to the first two questions, it's important to define two key terms. So in energetics, we refer to the system and the surroundings. Now, the system are the chemicals that are reacting, the atoms and the molecules. And the surroundings is everything else. So, for example, it might be the test tube. It might be the air surrounding the test tube. It might be the beaker that the chemicals are in. That is the surroundings. The system are the actual chemicals, the atoms and the molecules. Now, the first question is asking you to explain the difference between an endothermic reaction and an exothermic reaction, and it's a one-mark question. So an endothermic reaction is a reaction where the system takes in heat from the surroundings, and an exothermic reaction is a reaction where heat is given out from the system to the surroundings. So an endothermic reaction is accompanied by a temperature drop because heat has been taken in by the chemicals from the surroundings. And remember, when you measure the temperature, you're measuring the temperature of the surroundings. And an exothermic reaction is a reaction where heat is given out from the system to surroundings. So therefore, there is a temperature increase because the chemicals are giving out heat to the surroundings and you're measuring the temperature of the surroundings when you carry out an energetic experiment. Now, question 2 is asking you to draw an energy profile diagram for an exothermic reaction and then an endothermic reaction. So an energy profile diagram follows the energy that the system has, the chemicals, the molecules and atoms, during the course of a reaction. So I've drawn an energy profile diagram here for an exothermic reaction and an endothermic reaction so you can compare them. And you can see that we have the products having less energy than the reactants in an exothermic reaction because energy has been released to the surroundings. Now you'll notice if we look at the energy profile diagram for an endothermic reaction that the products have more energy than the reactants, and this is because the system has taken in heat from the surroundings. So therefore the products have more energy than the reactants. Now you'll notice on both diagrams that I've marked in the activation energy, and that is the minimum amount of energy required for a reaction to start. And it's like an energy barrier that the atom and molecules need to have a certain amount of energy before they react and they form products. Now it's also worth mentioning here that when we have an exothermic reaction, the enthalpy change delta H will be negative. And this is because energy is being given out to the surroundings. And when we have an endothermic reaction, because energy is being taken in, the delta H value is positive. So here's our next set of practice questions. Once again, read through the questions, pause the video, have a go at them, and then we'll go for the answers. Now question 3 says if we are to compare the enthalpy changes of various reactions, we must use standard conditions. So it's asking you to list these standard conditions. So the temperature would be 298 Kelvin. Now remember 273 is 0 degrees C. So 298 Kelvin is 25 degrees C. It would have a pressure of 1 atmosphere at standard conditions, and if we're dealing with concentration, that would be 1 mole per decimeter cubed. So those are the standard conditions, and if you had one of them correct, you get 1 mark. If you get all 3 of them, you get 2 marks. Now at AS level, we came across the term enthalpy, and enthalpy is the heat content of a system at constant pressure, and we also came across enthalpy changes such as the standard enthalpy change of formation, which is the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions and in their standard states. And we're asked here to write chemical equations to show the reactions that the following enthalpy changes represent. So the delta HF for C4H10 could be represented by 4C plus 5H2, and that goes to C4H10. And remember, it's important that you have 1 mole of a compound being formed in these equations. And for B, we have delta HF for NaCl. So remember, we can have 1 mole of NaCl here, and I just write down the elements that form sodium chloride. So I'd have Na plus half Cl2 that would form 1 mole of NaCl. So for C, I'm writing an equation to represent delta HF for water. So I form 1 mole of water. So my elements are hydrogen and oxygen. And to balance this, I need to put a half in front of O2, because remember, I can't put a number in front of H2O because I'm forming 1 mole of it. So it'd be H2 plus half O2 forms H2O. And for D, we have to write an equation to represent the delta HF value for H2SO4. So we have H2 plus S for sulfur plus O2 forms 1 mole of H2SO4. And remember, I have to have 1 mole of my product here because that's what the definition is. It's forming 1 mole of a compound. So therefore, I have to balance this. So I'm going to put a 2 in front of O2, and then I'll have 2 hydrogens, 1 sulfur, and 4 oxygens on both sides of the equations. So there's 1 mark for each correct equation here. So here's the next practice question we like to have a go at. So read for the question, pause the video, have a go at it, and then we'll go for the answers. So question 5 is about the standard enthalpy change of combustion, and this is another key enthalpy term that we covered at AS level. So it's asking you to write chemical equations to show the reactions that the following enthalpy changes represent. And remember that the standard enthalpy change of combustion is the enthalpy change when 1 mole of an element or compound reacts completely with oxygen under standard conditions. So question A is asking you to write an equation to represent the delta HC for ethanol. So I have to put 1 mole of ethanol here. I have to react it with oxygen, and my products are going to be carbon dioxide and water, and I know this because that's what forms when an alcohol burns. And then I just have to balance this, but I cannot put numbers in front of ethanol because I have to burn 1 mole of it in oxygen. So therefore, I'm going to put a 2 in front of carbon dioxide to get the carbons to balance, and then I'm going to put a 3 in front of the water to get the hydrogens to balance, and then I have 6 hydrogens on the right hand side, and I have 6 hydrogens on the left hand side, and if I put a 3 in front of O2, the oxygens are balanced as well. And for B, I'm asked to write an equation for ethane. So once again, I have 1 mole of ethane here, C2H6. I react it with oxygen, it forms carbon dioxide and water, and then I have to balance it without putting a number in front of ethane because that has to be 1 mole. And therefore I put a 2 in front of carbon dioxide, I put a 3 in front of water. That will give me 2 carbons on either side of the equation, 6 hydrogens on either side of the equation, and I put 3.5 O2 because I need 7 oxygens on either side. And for my next one, I'm doing an equation for the enthalpy of combustion of hydrogen. So that would be burning 1 mole of hydrogen in oxygen, so it would be H2 plus O2 forming water. And once again, I can't put a number in front of H2 here, so to balance it, I just have to get the oxygens the same number. So I'm going to put a half in front of O2, and then I'll have 2 hydrogens on either side. I will have 1 oxygen on either side of the equation. And for my last one, I have to write an equation for the enthalpy of combustion of carbon, and therefore I have 1 mole of carbon in my equation. I can't put a number in front of carbon here, and I have 1 carbon on either side of the equation. I have 2 oxygens on either side of the equation, so it's balanced. So my equation will be carbon plus O2 forms CO2. So this question is a 4-mark question. There's 1 mark for each correct equation here. Now at Hess level, one of the most important concepts you would have covered in energetics was Hess's Law. Now Hess's Law, which was formulated in 1840, helps us to calculate enthalpies for chemical reactions. And it states that the enthalpy change is the same for a reaction whether it occurs in 1 step or a number of steps. So here we have A go into D, and the enthalpy for that, delta H4, is equal to delta H1 plus delta H2 plus delta H3. And that's because the enthalpy change to go from A to D would be the same if I went to A to B to C to D, because it doesn't matter if I go in 1 step or a number of steps, the enthalpy change is the same. Now an advantage of Hess's law is that we're able to calculate enthalpy changes without having to carry out the reaction. So if we use this example and we're looking at delta H4, the enthalpy change from A to D, we don't have to carry out that reaction of converting A to D in 1 step, because we can just work out the enthalpy changes of A going to B, and then B going to C, and C going to D, and by adding them up we can calculate the delta H4 value, the value from A to D. And this is useful because it might be that the reaction converting A to D might be violent or too dangerous for us to carry out, or it might be over too quickly. So Hess's law enables us to still find out the value of delta H4 without us having to complete this reaction. So now let's do some revision of Hess's law and energy cycle diagrams with some practice questions. So here's the first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answer. Now in question 1, I have to use the values given in the enthalpy cycle below to calculate the enthalpy of combustion of carbon disulfide, delta Hc in kilojoules per mole. So I already have the enthalpy cycle or energy cycle drawn for me. So I just have to go from reactants to products here. So I'm really going from the CS2 and O2 to my products, CO2 and 2SO2. And it doesn't matter if I go in 1 step or a number of steps, the enthalpy change is the same. So here I have an arrow in the opposite direction that I want to go. So therefore I just need to change the sign of the value here. So instead of it being plus 90, I want to go in the opposite direction here. So it would be minus 90 kilojoules. Now, the other 2 arrows are in the same direction that I want to go. So all I have to do to work out the delta Hc value here is just to add these values together. So it would be minus 90 plus minus 394. I don't have to change the sign of this value because it's in the same direction as I want to go. And then I have to add it to 2 lots of minus 297. And once again, I don't change the sign of that value because once again, the arrow is pointing in the direction I want to go. So this can be simplified as delta Hc equal to minus 90 kilojoules per mole minus 394 kilojoules per mole minus 594 kilojoules per mole. And that would give me a final value equal to minus 1078 kilojoules per mole, and you can see that this is a minus value for delta H, so it's an exothermic reaction. So here's our second practice question. So once again, read through the question, pause the video, have a go at it, and then we go for the answer. So in question 2, I'm asked to use the standard enthalpy change of formation values given in the table to calculate the standard enthalpy change delta H for the above reaction. So the delta HF values are the enthalpy change when you form 1 mole of a compound from its elements in their standard states under standard conditions. So here we have 2CHClF2 go into C2F4 and 2HCl. So I'm going to write down elements in their standard states, just to remind me that the delta HF values are the enthalpy changes to form 1 mole of a compound from the elements in their standard states. So I'm going to then draw arrows to represent the delta HF values here, because the delta HF value of CHClF2 is minus 502. So I'm drawing an arrow from elements in their standard states to CHClF2. And because I have 2 moles of CHClF2, it's 2 lots of the delta HF value that I need. So it's 2 times minus 502. Now because I'm forming 1 mole of C2F4 here, I just need 1 lot of the delta HF value of it, minus 659, and then I'm forming 2 moles of HCl, so I need 2 lots of minus 92. Now all I need to do then to calculate delta H is to find a route around my enthalpy cycle. So I'm going to go from reactants to products. And you can see that the arrow here from elements in their standard states to 2 lots of CHClF2 is in the wrong direction for me. So I need to change the sign. I need to change the sign of the delta HF value. So I have 2 lots of 502, not minus 502, and that would be 1004. And then I'm going to add it to the other values. Now the other arrow's in the same direction that I want to go. So I'm going to add it to minus 659. I'm going to add it to 2 lots of minus 92. So if we simplify this, delta H is equal to 1004 minus 659 minus 184. And if I put these values into the calculator, I get a value equal to 161 kilojoules per mole. And because this value is positive for delta H, it's an endothermic reaction. So here's the third calculation for you to attempt. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answer. So for question 3, I'm asked to use the table of standard enthalpy changes of formation, delta HF values, to calculate the standard enthalpy change for the reaction above. So once again, I'm going to write out the equation here that I'm trying to find the delta H value for. So it's 2 lots of NO plus Cl2 forms 2 NOCl. And then because I've been given the delta HF values, that's the enthalpy change when you form 1 mole of a compound from its elements in their standard states. I'm just going to write elements in their standard states to remind me of this. And then I'm going to draw an arrow from this to everything in the equation. So I have 2 NO here, and I'm given the value for the delta HF to form 1 mole of NO, but I need to form 2, so it's 2 lots of 91. And then the enthalpy of formation of an element is 0, because you can't form an element from its elements. And the enthalpy change to form 2 moles of NOCl is equal to 2 lots of 53, because I have the value to form 1 mole of NOCl. Now I just have to find a route round this diagram from reactants to products. So delta H is going to be equal to, now I've got to change the sign here for my value to go to form 2NO because it's in the wrong direction. I want to go the opposite way. So I'll have two lots of minus 91 here instead of 91. So that would be equal to minus 182. And then I need to add it to my value to form 2 moles of NaCl, which will be 2 lots of 53. And I don't have to change any signs there because the arrow is in the direction I want to go. So it'll be minus 182 plus 106, which will give me a final value equal to minus 76 kilojoules per mole. And as the value is negative for delta H, it is an exothermic reaction. So here's our final practice question. So once again, read for the question, pause the video, have a go at it, and then we'll go for the answer. So for question 4, I'm asked to use the standard enthalpy change of formation values here to calculate the standard enthalpy change of combustion of octane. Now octane is C8H18, and if I'm going to write an equation to represent the enthalpy change of combustion, I'm going to react it with oxygen to form carbon dioxide and water, and I just have to balance it here. Now remember, I have to have 1 mole of octane, so I can't put a number in front of that. So therefore, to balance it, I put 8 in front of the carbon dioxides to get 8 carbons on either side, and I put a 9 in front of water to get 18 hydrogens on either side of the equation, and that will give me a total of 25 oxygens, so I need 12.5 O2. Now because I'm being given delta HF values, and the delta HF value is the enthalpy change when you form 1 mole of a compound from elements in their standard states under standard conditions, I'm going to write the words elements in their standard states, and then I'm going to draw arrows from these words elements in their standard states. So I'm going to draw an arrow to C8H18, and I already have the value for this arrow, which is minus 250, and that's the enthalpy change of formation for C8H18, and I'm forming 1 mole of it, so it's just 1 lot of minus 250. The enthalpy change of formation of oxygen is 0 because it's 0 for an element. And then I just have to work out the values for 8 lots of carbon dioxide and 9 lots of water. And I'm given the delta HF values for both compounds. So I need 8 lots of minus 394 because I'm forming 8 CO2s. And I need 9 lots of minus 286 because I'm forming 9 H2O. So delta H is equal to, now all I have to do here is find a route around my diagram, and I'm going from reactants to products once again. So the first arrow is in the wrong direction that I want to go, so I have to change the sign here, so I can't have minus 250 because that's not the direction I want to go. I want to go the opposite way, so it's plus 250. And then the other 2 arrows in the same direction I want to go, so I'm going to add these together. So it'd be 8 lots of minus 394 added to 9 lots of minus 286. Now if we simplify this, delta H for this reaction is equal to 250 kilojoules per mole minus 3,152 kilojoules per mole minus 2,574 kilojoules per mole. And that will give me a final answer equal to minus 5,476 kilojoules per mole. And you can see that it's a minus value for delta H, so it's an exothermic reaction. So that concludes this video lesson. So after watching this video, you should now have an improved understanding of key energetics concepts covered at Hess level, such as energy profile diagrams, enthalpy changes, and Hess's Law. And you should also be able to use and draw energy cycle diagrams applying Hess's Law to calculate enthalpy changes. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.